Hornets, thank you for joining me today. Today we're going to be taking a look at our pretest, basically a review of trigonometry that we have thus far. I've given you two different pretests, and this is but the solutions to the first. I have put them online, so hopefully you can follow along with me as I go through and do the work. So we're going to go ahead and begin with our first question, which is, what do we do when we see if x equals 8 secant theta? Use trigonometric substitution to rewrite the square root of x squared minus 64 as a trigonometric function of theta, where theta is between 0 and pi over 2. Now, whenever you want to start this, please remember it can be any of the Pythagorean identities that we have. So we could be replacing 1 minus sine squared, we could do 1 minus cosine squared, we could do 1 plus cotangent squared, we could do secant squared minus 1, cosecant squared minus 1, etc. Okay, so just be aware. There are lots of different substitutions, and our goal is to try to factor out any coefficient or GCF, and then from that, use our identities to replace with a square piece that we can take the square root of. Now, this is going to give us an absolute value unless we have a situation like we do now, where we're always going to have a positive value within the domain given. If the domain changes between positive and negative, an absolute value is going to be required. So we're going to go ahead and we're going to start. Now, when you write this down, always use parenthesis and then put your squared minus 64. We're going to put the x inside. So x secant of theta. Now we're going to simplify this, so we end up getting the square root of 64 secant squared of theta minus 64. We're then going to factor out the GCF of 64, so that we have the square root of 64 times secant squared theta. Let's try that again, Mr. Lamb. Secant squared theta minus 1. Now this is our identity that tells us that we have a tangent squared. So I'm going to call it the square root of 64 times the square root of this identity, tangent squared of theta. When I end up getting 8 absolute value of the tangent of theta, I then look at my domain. I then drop the absolute value because the domain is such that no matter what value of tangent I use, I will always get a positive value. That's number one. Number two, notice we have a cosine on both sides. Do not try to use a double angle and work backward. Don't try to use the product sum. Move the root 3 cosine over. Since we have a cosine of theta that appears twice now, notice the minus root 3 cosine theta. Now that it equals 0, we can factor out the cosine of theta. This is going to leave us with 2 sine theta minus root 3. We're now going to set each factor equal to 0. That means that the cosine of theta is going to equal 0, and the 2 sine of theta minus root 3 is equal to 0. Now, because I have the cosine, I'm going to look at it, I'm going to say, hey, when is cosine 0? That's when we're straight up and down on our axis, the y-axis. And it could be up at the top or the bottom. These two in degrees are 90 degrees and 270 degrees. If we are asked to use radians, I would use pi over 2 and 3 pi over 2. Both of these answers are going to be acceptable. We then go to the second part. We're going to solve for sine of theta by adding root 3 and then dividing by 2. Notice we now have the sine of theta as root 3 over 2. Once again, we think about our identity or our ratios, and we should get 60 degrees. This is in the first quadrant, and then we have 120 degrees in the second quadrant. If you're dealing with radians, this would be pi over 3 and 2 pi over 3. These are now the solutions that I would then probably put in the solution set from my smallest to largest. So pi over 3, pi over 2, 2 pi over 3, and 3 pi over 2. And this is my solution. Once again, there are no extraneous values here. We have no situation where we have an undefined situation, and that's what our answer would be. Now, please remember, if you think you have an extraneous solution, plug it back into the original function and check to see if you get the same answer. This does require you to use your ratios, so make sure you have studied them. Number 3. Notice in number 3 we have a quadratic cosine and we have a cosine that's to the first power. I'm going to rewrite this as a cosine quadratic, or quadratic of a trigonometric function. To do that, I'm simply going to subtract 5 and set it equal to 0. I'm now going to factor it as if the cosine were a variable like x or an a. This is where I was telling people you can use the u substitution and let u equal the cosine of x. That would then give you 3u squared plus 2u minus 5. You would then back substitute after you have factored. Now you can also factor it as it is, and some people are going to be proficient with that. Not everybody will. Please don't think that's a deficiency. It just means that you're not quite prepared yet and more practice would be required. You can still use that u substitution to make up and compensate for that lack of practice. We then have to make sure that we get a positive 2. So I'm going to have a 5 and a 1, positive and a negative. I'm now going to take each factor, set it equal to 0, and solve. Notice when I do the first one, cosine of x is going to end up being 5/3. This poses a problem because the range that we are allowed to work with for a cosine is -1 is less than or equal to the cosine of theta, which is less than or equal to 1. We have to have an answer that can equal -1 or 1, and it has to be in between. 5/3 is 1 2/3, and that's too large. It does not work, and therefore no solution. Notice this isn't what we call an extraneous solution. It simply doesn't exist. Cosine of x plus 1 equaling 0 means that the cosine of x is equal to -1. We know that the cosine of x is going to be equal to -1 at 0 degree, it should be a positive 1. Did I do that correctly? Let me double check. Up. I have my signs backward. That's going to be a problem. So for those of you who are just saying, hey, wait a minute, Mr. Lamb, there's an issue with your factoring. Yep, you were right, and I'm now correcting it. That's going to mean that this was a plus, giving me a minus. It still is a no solution, but now it's correct. We're now looking at our cosine of x equaling 1. When is cosine of x equaling 1? In degrees. This is 0 degrees. Therefore, my only solution is 0 degrees. Going to number 4. Notice that I have a cosine squared x equaling 3 sine squared x. And I'll be very honest with you, the best way for us to deal with this is to turn it either into a cotangent squared, which would equal 3, or a tangent squared, which equals 1/3. I prefer to work with the tangent squared, so I'm going to divide both sides by cosine. Notice that's going to leave me with a 1 equals 3, and I have sine squared of x over cosine squared of x. I'm then going to divide by 3 so that I have 1/3 equals the sine squared of x over the cosine squared of x. That means I have 1/3 equaling the tangent squared of x. I'm going to take the square root on both sides, and I end up with 1 over root 3, which we will call root 3 over 3. This is equal to the absolute value of the tangent of x. When I drop the absolute value, I'm talking about a plus or minus for the tangent of x. And now I'm looking in each quadrant. We know the reference angle for a root 3 over 3 is pi over 6 in radians. And then we want to get the negative. Well, when we have a negative root 3 over 3 in the second quadrant, that's going to be 5 pi over 6. Having a positive in the third quadrant is going to be a 7 pi over 6. And then a negative again is going to be in the fourth quadrant, and that is 11 pi over 6. Once again, these are straight equations. There's nothing bizarre to them. We aren't looking at anything that could cause a problem, and so we have our solution. Next. Just as we saw all the way back up in number 2, where I have cosine and a cosine on each side, we now have a sine cubed and a sine on each side. I want to get them onto the same side, and I'm going to factor the sine of x out. So I end up with the sine cubed of x minus the sine of x equaling 0. When I factor out the sine of x, I notice that I am left with a difference of squares. Therefore, I'm going to go ahead and factor it into a plus b, a minus b. This is the sine of x times the sine of x minus 1 times the sine of x plus 1. I'm now going to set each of these to my 0, so each factor is equal to 0. That means I have the sine of x minus 1 is equal to 0, and the sine of x plus 1 is equal to 0. Now, if you had attempted to take this piece right here, sine squared x minus 1, and take the square root after moving the 1, you will still have the same answers, but it will require you to remember that you get the absolute value for the sine of x when you take the square root of sine squared. When you drop the absolute value, we get positive and negative 1, and it allows you to find them. So we ask, when is sine going to be 0 in degree mode? Well, sine is 0 at 0 pi, 0 pi, which would be 0 degrees. And then we have at 180 degrees, which is also pi for those of you doing in radians. This then allows us to solve for sine of x. It equals a positive 1. We know sine of x equaling a positive 1 is at 90 degrees. And then we would do the same thing for the sine of x equaling negative 1, which is at 270 degrees. I'm then going to list my answers from least to greatest: 0 degrees, 90 degrees, 180 degrees, and 270 degrees. There is my answer, and I'm ready to move on to number 6. Notice number 6 is already written as a difference in squares, so I'm going to want to factor it. This is going to give me 2 cosine of x, and I have a plus 1 and 2 cosine of x minus 1. I set each factor equal to 0, so 2 cosine of x plus 1 equals 0, and 2 cosine of x minus 1 equals 0. This gives me cosine of x is equal to a negative 1/2, and the cosine of x is equal to a positive 1/2. I'm now going to stop and think about the positive 1/2 first. We know that this is in pi over 3 reference angle, and we want to find it also in the fourth quadrant, which is 5 pi over 3. Then we want to find the negative. This is going to give me 5 pi over 6. And 7 pi over 6. And then just going to go ahead and list them from least to greatest: pi over 3, 5 pi over 6, 7 pi over 6, and we finish with the 5 pi over 3 in the fourth quadrant. And those are my solutions. Let's now take a look at number 7. Now, when I'm working with number 7, you'll notice that I see the sine of 2x. One of the formulas that I have asked you to memorize and make sure you know is the double angle formulas. So, by putting cosine of x equaling the double angle identity for sine 2x, I get 2 sine x cosine x. And I'm now looking at one of the problems that we had in number 5, where we had sine on both sides, or number 2, where we had the cosine on both sides. Here we have cosine on both sides, so I'm going to subtract the cosine so that I have 2 sine x cosine x minus cosine x. I'm then going to factor out the cosine, leaving me with 2 sine x minus 1. I'm now going to set each factor equal to 0, and I'm going to solve. Now you'll notice that we do not have it in either radians or degrees, nor do we have a domain. So I'm looking at plus 2 pi k, and I have 2 sine of x minus 1 equals 0. So I'm going to think about it in terms of radians. My cosine is 0 at pi over 2 and 3 pi over 2. You'll notice that these are separated by pi. So I have x sub 1 is going to be pi over 2 plus 2 pi k. Let's change that to pi k as it's 180 degrees apart, and that would just be pi k. Alrighty, if I'm doing degrees, I'm looking at 90 degrees plus 270 degrees, and x sub 1 would end up being 90 degrees plus 180k. Once again, they're separated by 180 degrees. We're now going to go to the second part. This is where we have the sine of x, when I solve it, equal to 1/2. And we know that sine of x is equal to 1/2 at pi over 6. This is now my second solution, and I have pi over 6 plus 2 pi k. And I would have my third solution, and this would be x sub 3 equals, and this is now in the second quadrant, 5 pi over 6 plus 2 pi k. Now, if I'm working with my degrees, I would have, 30 degrees. So x sub 1 is going to be 30 degrees plus 360 degrees k. And I have 150 degrees plus 360 degrees k. Now, if I were just looking for a single answer, I would then list my 30 degrees first. I would then follow by the 90 degrees, then follow up with the 150 degrees, and then finish with 270 degrees. Now, once again, this is just between 0 and pi over 2, 0 and 2 pi, or 0 degrees and 360. Now, luckily, I'm not asking you to find the specific angle identity that we would have. Let me just get out all of my wonderful identities that I have. And I have put them away. I was using them just a moment ago. I'm just going to pause. Alrighty, I've taken the opportunity to take that brief moment in order to find my product, sum, and difference. And you'll notice here we have from my sum or difference to my product. Now, this is the formula that was given in the book. Otherwise, I would be using mine, and I would have the 2 dividing both sides. I have a cosine minus a cosine, and I would set each of them equal, and then I would do a system of equations and solve for the alpha, then plug it back in and solve for the beta. The book gives you formulas that are already set up for you. So with the cosine of alpha minus the cosine of beta, I can go ahead and just simply use it and say I'm looking at minus 2 sine of 3x, let's try that again, 3x plus x divided by 2 times the sine of 3x minus x divided by 2. And I'm going to go ahead and I'm going to slowly simplify it. And we are saying that it equals 0. So I'm left with negative 2 sine of 4x divided by 2, which is 2x, and the sine of 2x divided by 2, which is x. It is with these that I can now find all of my solutions. First of all, I would start by saying, when is the sine of x equal to 0? Now we know that the sine of x is going to be equal to 0 at 0 pi and at pi. Now I would point out we could check our answer, 3 pi and pi. That's going to give me a -1 and a -1 with the double negative will make it 0. 0 minus the 0 is going to be a sine of 0 is 1, minus 1 is also 0. So both of these solutions will work. When we have the sine of 2x equaling 0, we're now dealing with our rotations. We know that we're dealing with sine being 0 at 0 and pi in radians. So I have my same answers, 0 pi in plus 2 pi k is equal to 2x. That means that my first group of x's is going to end up being 0 pi plus pi times k. Doing this again, but with the second solution, or the second possibility of pi, I have 2x is equal to pi plus 2 pi k. Make sure you can see that. I'm going to divide both sides by 2, and x is now pi over 2 plus pi k. I now have all of my solutions that I could hope for. All right, let's just go ahead and make sure that they're within 2 pi. So I have 0 pi, pi. They're the same as what I had here. Then I have pi over 2 and 3 pi over 2. These will then be the solutions which I will list, and I end up with 0 pi, pi over 2, pi, and 3 pi over 2 as my solutions. Once again, a quick check by plugging these values in will confirm that they are indeed correct. This brings us to the second page, or turning it over. You'll notice that we are going to start off right back at the beginning of this chapter. We are told that we have an angle right here. When sine is positive and tangent is negative, we are looking at the second quadrant. So we're going to go ahead and we're going to draw a reference angle in the second quadrant, right angle, and we know that our hypotenuse is 13, and the opposite of the reference angle for u is going to be the 5. This is a 5, 12, 13 triangle, and we know that in the second quadrant, our cosine is negative. This allows us to now find that the sine of u is equal to 5/13. The cosine of u is equal to -12/13, and that the tangent of u is going to end up being a -13/12. Then we look at the second part, and we see that we have a cosine that is negative and a sine that is negative. This is in the third quadrant. So I set up my triangle in the third quadrant. Here is V all the way through, and I'm going to make sure that I have my cosine is -4 and a 5. Notice the hypotenuse is always the positive piece. We're now looking at a Pythagorean triplet, and we know that it's a 3, 4, 5 triangle, and in the fourth quadrant we want a negative. This tells me that the sine of V is going to end up being -3/5. The cosine of V, we've already been told, is -4/5. And the tangent of V is going to end up being -3 over -4, which is 3/4. Alrighty, my lights went off, so I had to take a moment and find them, or turn them back on again, I should say. Find the light. Alrighty, here we go. So I'm going to be using the formula that I've asked you to memorize, which is the sum formula. This is going to be my sine of u, cosine of v, plus the cosine of u sine of v. And we have each of these that we're going to put directly into our sum. Since the sine of u is 5/13, that's going to go first. The cosine of v is negative 4/5. The cosine of u is negative 12/13. And the sine of v is negative 3/5. I'm now going to end up getting a common denominator of 65, and I have a negative 20, and I have a positive 36. I end up getting the answer 16/65. Now, in order to find your cosecant, all you do is take the reciprocal, 65/16. Then move on to the next problem. Cosine u plus v. This is cosine u cosine v minus sine u sine v. We're now going to do a direct substitution again. And as I do this, I end up having the cosine of u, let's find it, negative 12/13. Cosine of v is negative 4/5. Sine of u is going to be positive 5/13. And then we have the sine of v, which is negative 3/5. I end up getting 48/65. And I am subtracting a double negative to make it a positive 15/65. I'm now going to add them together, and I get an answer that is 63/65. To do my secant, I take the reciprocal, 65/63. Now, for the last part, I have a couple of options. Now, because I already have the sine and the cosine, it doesn't make much sense to do a lot more work. You do not have to use the tangent formula. We know that the tangent of u plus v is the sine of u plus v over the cosine of u plus v, and we have both of them. So if I take my sine, 16/65, and I divide by my cosine, 63/65, I end up having 16/65 times 65/63. The 65s automatically cancel, and I have 16/63. Then I take the reciprocal for my cotangent for 63/16. Now, for those of you who have decided to do it the longer way, which is what I did in the answer key that I provided online, I'd like to simply show you. We use our formula. Once again, this is going to be ugly if you try to do it, and you probably don't want to. I take tangent u plus tangent v over 1 minus tangent u tangent v. I substitute with the given information that I have here and here, and I end up having to simplify. Now notice this is going to give me a 48 plus 15 all over 48. That's 63/48. And up top, we're going to have, in terms of 48, negative 20 plus 36 over 48. We simplify it. The 48s cancel, and we're left with 16/63. It's the same answer. You have to decide, which one do you want to do? One does have more work to it, and so I do recommend you are more careful. We're going to go to number 10. In number 10, I'm looking at my alpha angle here and a beta angle here. Now, be aware, we are assuming that our arc cosine is currently positive, but there's no way for us to know. It is entirely possible that it will be in the second quadrant as opposed to the first, and then we have different ratios. For this test, we are going to make the assumption, or follow the assumption, that it is in the first quadrant and in the first quadrant. We're going to find, therefore, each of these. We have 1/2, 2, Here's my alpha, here's my beta, here's my 5, here's my x. Oh, pardon. Let's try that again. X for the cosine is the adjacent side. Sine has a 1. We use our Pythagorean theorem to find root 3 and the square root of 25 minus x squared. This is a squared minus b squared, a squared plus b squared equals c squared, or a squared equals c squared minus b squared. I'm now going to find my sine of alpha and my cosine of alpha. Sine of alpha has to be the 1/2, and the cosine of alpha is the root 3 over 2. Then we have our sine of beta, and the sine of beta is this square root of 25 minus x squared over 5, and the cosine of beta is going to be the x over 5. Now you'll notice if the arcsine of 1/2 is the alpha and the arc cosine of x over 5 is the beta, I'm really looking at the cosine of alpha minus beta. We're going to write that formula down. Cosine alpha, cosine beta, plus sine alpha, sine beta. Since I know what each is, I'm going to replace them directly. Here we go. Root 3 over 2 is the alpha for cosine. The x over 5 is our beta. Then we have, for our sine of alpha, is 1/2. I'm going to need a little bit more room. And I'm looking at the square root of 25 minus x squared divided by 5. We're now going to get the common denominator of tenths. We have x root 5, and we're going to add the product, which is the square root of 25 minus x squared. This is the answer, and I would stop right there. There's no need to go further. We're now going to go ahead and we're going to take a look at number 11. Now, when you see the sine of x plus the cosine of x equaling 1, it only makes sense that we square both sides. This is going to give me the sine squared of x plus 2 sine x cosine x plus cosine squared x equaling 1. Notice that sine squared and cosine squared, when added together, give us 1. So we're going to group them together. Then have our plus 2 sine x cosine x, and it equals 1. We then get, with our Pythagorean identity, 1 plus 2 sine x cosine of x equaling 1. The 1's will cancel when I subtract them, and I'm left with 2 sine of x cosine of x equaling 0. That means I'm going to take each factor, set it equal to 0. The first one is the sine of x equaling 0. The second is the cosine of x equaling 0. Now, when I plug in or try to solve, I know that I'm dealing with let's see, 0 is going to be 0 degrees, 180 degrees, cosine being 0 is 90 degrees, and 270 degrees. Now notice, when I plug in the 0 for my sine and the 0 for my cosine, I end up getting 0 plus 1 equals 1. That is a valid solution. If I plug in 150, the sine of 150 is going to end up being a positive 1/2, and the cosine of 150 is going to be a negative 1/2. So we can clearly see that the 3 pi, hang on a minute, let me double check that a minute. I want it to equal 1, not 0. So let's check this again. That was 0 plus 1 is 1, that checked. But if I put in the pi over 3, 2 pi over 3 and 2 pi over 3, the 150 degrees, 150 degrees isn't going to work. Okay, think about it. The sine of 150 degrees is 1/2. The cosine of 150 degrees is negative 1/2. That gives me 0, not 1, and therefore this fails. It is what we call an extraneous solution. When we do 90 degrees for the sine of x, so sine of 90 degrees is 1, the cosine of 90 degrees is 0, 1 plus 0 is indeed 1, 90 degrees is a valid answer. If I put in 270, I now get negative 1 plus 0, and negative 1 doesn't equal 1, so 270 is not a valid answer. Since we want to have all of our solutions, notice there is no domain. I'm looking at 0 pi plus, and I'm looking at 2 pi k. That's going to be my first solution for x. The second solution for x is the 90 degrees plus 3, and I need to put it in degrees, Mr. Lamb. 360 degrees. Now remember, if you prefer radians, you can always convert these into radians. I'm just trying to be consistent. So I have 360 degrees K. And those are my two solutions. That's what I'm looking for. The key here is to double check by doing a check and plugging in your initial solutions into the original equation and then add your period. For number 12, notice number 12 has that sine of x over theta. So I'm going to go to my half angle formulas, and I'm going to look for the sine of alpha divided by 2. I have plus or minus the square root of 1 minus cosine alpha over 2. That's what I'm going to plug in. So I have plus or minus the square root of 1 minus cosine of x divided by 2 equaling the cosine of x. I'm going to square both sides so that I have 1 minus cosine of x divided by 2 equals cosine squared x. I'm going to multiply both sides by 2. Cosine x is equal to 2 cosine squared x, and I'm now going to move everything over so it equals 0. 2 cosine squared x plus cosine of x minus 1. I can now factor it like a quadratic. So 2 cosine of x, I know I'm going to have a 1. I have a cosine of x, I know I have a 1, and I have to end up with a positive. So the 2 cosine of x is multiplying by a plus 1, and the cosine of x is multiplying by a negative. I'm now going to solve. I have 2 cosine of x minus 1 equals 0, and I have cosine of x plus 1 equals 0. This gives me the cosine of x equaling negative 1, and we know that the cosine of x equals negative 1 at pi. I then go ahead and I'm going to check. This gives me the cosine of x equaling 1/2. We know the cosine of x is 1/2 at pi over 3 and 5 pi over 3. We now want to go back and check with the original equation. When I plug the pi over 3 in, I'm left with the sine of pi over 6. Does it equal the cosine of pi over 3? The answer is yes. We have 1/2 equals 1/2. Let's now check that with 5 pi over 3. The sine of 5 pi over 6 equaling the cosine of 5 pi over 3. Now we know that the sine of 5 pi over 6 is 1/2, and we know that the cosine of 5 pi over 3 is also 1/2, and therefore this is a valid solution. Finally, we have to check pi. So we take our sine of pi over 2, and we compare it with the cosine of pi. Notice, sine of pi over 2 is 1, but the cosine of pi is negative 1. This is not correct. They are not equal. It is an extraneous solution, and the only two answers are pi over 3 and 5 pi over 3. And these are my solutions for number 12. Alrighty. I hope this has helped. I hope it's given you some insight of how we're using our identities and how we're trying to make this work. Please remember, when you are working with the tangent of u plus v, you can work with the sine of u plus v divided by the cosine of u plus v. And because you already have those two answers, it is more simple to work with. If you would rather use the tangent identity, that is entirely up to you. But please be careful. I don't want you to lose points because you make a silly mistake. Alrighty. Thank you, Hornets. That's it for the day. I hope that this has helped you. Please remember, if you found this useful, please click like. If you have suggestions, feel free to give them to me. Otherwise, that's it. We'll put the part 2 or the second practice test online tomorrow. Be well, take care, and have a very good evening. Bye-bye now.